Alright, so this is section 1.1, derivatives intro, slope of the tangent line at a point. Okay, we'll come to that. So firstly, I want you guys to do this warm-up. So I want you guys to evaluate this limit here. So take a second, pause the video, see if you can do it. Again, I'm assuming you guys have learned limits. So this should be no problem. But why don't you try it? If not, just unpause the video and we will do it together. So go ahead, pause the video. Try it on your own. Okay, assuming you've tried the problem, let's go ahead and do this here. So limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So looks very confusing. Again, we'll get to the meaning of this, but like for now, I just want you to do the problem. So f of x plus delta x, please do not get confused by this. F of x plus delta x, literally, it's just function notation, right? So if we do f of x plus delta x, we're literally plugging in, x plus delta x into f of x. So what I mean by this is f of x plus delta x, it'll literally just be x plus delta x squared, because we're putting in x plus delta x in for our x, right? And f of x is x squared. So now f of x, hopefully know that f of x is just x squared, right? That's given to us right here. Okay? And so now if we just put all the pieces together, we get the limit as delta x approaches 0 of f of x plus delta x, which you said was x plus delta x squared, and then minus f of x, which you said was x squared, and then all over delta x. And so now we just need to do some simplification here. So I'm going to expand this x plus delta x squared here into x squared plus 2x delta x plus delta x squared minus x squared all over delta x. And hopefully you see here that these x squareds will cancel. Okay, and so now we'll get limit as delta x approaches 0 of 2x delta x plus delta x squared over delta x. And so what I'm going to do here is split this into two separate fractions. Okay, so what I mean by that is we'll have limit as delta x approaches 0 of 2x delta x over delta x plus delta x squared over delta x. So I'm just splitting this guy into two separate fractions. And so now hopefully you see here that delta x will cancel this guy, and then this delta x will cancel the denominator, and then we'll get a 1 here instead of a 2. So then we'll get limit as delta x approaches 0 of 2x plus delta x. And so now we can just do a direct substitution here. If delta x is approaching 0, we can plug in 0 in for delta x. So then we'll get 2x, and then that's our answer. Okay, so this limit right here, this limit, right, is 2x. Okay, so what in the world does this mean? Okay, this looks really funky. Maybe you've heard of this specifically. This is your slope of the secant line. Again, it's your y2 minus y1 over x2 minus x1 written really differently. It's called, also known as the difference quotient. So maybe you've heard of this, excluding the limit part. Maybe you've done a limit exactly like this before, and your teacher is just trying to kind of introduce you to this idea. If not, that's fine. I showed you guys how to do this. You should be able to know how to do a limit like this specifically with the difference quotient here. So this is called the difference quotient. So maybe you've seen this before and you forgot, or maybe you've just never seen it before, maybe you've seen it before and you just forgot how to do it. I don't know. All right, but make sure you know this. It's important. So what does this even mean? Okay, so I mentioned again, I'm going to go back to this slide again. This right here, excluding the limit, let's forget the limit for a second here. Excluding the limit, this right here is slope of the secant line. And we're going to show you that right now. So let's draw a curve right here. Okay, we can even go with x squared. Why not? We just did that in our example. I think we should do x squared. So excuse me for my very bad drawing here. So let's draw x squared. Okay, very rough drawing here of f of x equals x squared. Okay, but function doesn't really matter. Just trying to illustrate what we're kind of doing here. So let's say that we have a point here called P, and we have a point here called Q. And I want to find the secant line, the average rate of change. Hopefully you've heard of this word, secant line. Maybe you have in geometry class, but essentially that's just average rate of change. The line, or just the line formed between the points P and Q. So I'm going to draw that here. Okay, this is our secant line, and so I actually want to find slope of this secant line. Okay, so in order to do this again, remember I'm going to write m secant here. M secant is just y2 minus y1 over x2 minus x1. Okay, you should have learned this in Algebra 1. It's just rise over 1. So how do we find our y2, y1, x2, x1? How do we find that? Well, I'm going to call this guy x. Okay, so its x value right here is literally x. So we plug in x into a function, our output should be, you guessed it, f of x. Okay? And then here, I'm going to call this x plus delta x. Okay, so delta x, like you saw here, right? This delta x, it means change in x. So this delta symbol, maybe you've seen it in like a science class, or you're just aware of it. Delta is just like change. We use it for describing change. So we're going to see why we use delta x here, and why we're changing something in just a second here. But yeah, we're going to use delta x because we're going to eventually change x. Some people use h as well. So, for example, you can see this as f of x plus h minus f of x all over h. In fact, when you're given just a difference quotient problem without this limit, you will just see it as f of x plus h minus f of x over h, typically. So sometimes you just use h, but in this case we're going to use delta x. Okay, so if I'm going to call this x plus delta x here, well, the distance between, of course, x and x plus delta x here, that distance is going to be delta x, right? Right. The distance between x and x plus delta x is delta x, and you can prove that by just doing x plus delta x minus delta x. That should give you x, so you're back to where you started. Okay, so now if we plug in x plus delta x, guess what our output should be, right? Since, assuming you're familiar with function notation, which I would be shocked if you are not, this would just be f of x plus delta x. So we have our 2 points technically, right? We have x comma f of x, and then x plus delta x comma f of x plus delta x. So now we're just going to do our y2 minus y1 over x2 minus x1. So I'm going to call this x1. I'm going to call this y1. Or no, I'm going to actually switch it around. Oops. I'm going to switch it around. I'm going to call this x1. Or no. I'm right. I'm going to call this x1. Sorry. Again, doesn't matter if you choose x1 to be this guy as well. You can pick x1 to be this. You can pick x1, y1 to be x plus delta x and f of x plus delta x. But I'm going to choose it to be this because it's easier. It gives us that f of x plus delta x minus f of x over delta x form automatically if we just do it that way. So I'm going to call this y1 because if you choose this to be x1 and y1, you will get it. It'll look different, but if you just factor out a negative, you can get it back to f of x plus delta x minus f of x over delta x. But it's still correct if you put this as x1 and y1. But I'm going to actually put this to x2 and y2. Okay, so then if we do m secant here, right, or m secant, it's just going to be y2, which is f of x plus delta x, minus y1, which is f of x, all over x2, which is x plus delta x, minus x1, which is x. So then you see here that these x's cancel, and then voila, we get f of x plus delta x minus f of x all over delta x. And that's exactly what we have here. So again, slope of the secant line is this. So now let's get to the limit. Let's get to the limit. Okay, so now, this is the secant line. We want to get the tangent line. Okay, we want to get the line tangent at x. We're going to choose x in this case, right? Because we're trying to make this general, right? We want to find the slope of the line tangent at any point, so we're going to call that x, okay? And we have to assume that, of course, there's a point that's greater than x. There's an x value that's greater than x, which is x plus delta x, and then, of course, f of x plus delta x. You get it. So, in order to do this, right, we want to find the tangent line at x. Okay, what does that look like? Again, confused. This is a secant line, right? I'm going to try to highlight this here so you can kind of see here. This is a secant. Whoops. What did I do? I have no clue what this is. Okay, this is a secant line right here. Okay, so now we want the tangent line. Okay, what does that look like? Well, a tangent line. A tangent line looks like this. Okay, so it's literally a line at a point, essentially. What it is. This is the tangent line. Okay. Let me maybe draw that a bit better. So the line tangent at P. Let me draw it a bit better here, but hopefully you get the point. It's literally the line at a point. So we're trying to find this slope right here. Okay, so in order to do this, again, that's where the limit comes in. This delta x, this distance from x plus delta x to x, we need this x plus delta x here. We need this x plus delta x to get closer to this x. So in order for this x plus delta x here to get closer to this x, this delta x needs to get smaller. So this delta x needs to get infinitely smaller. Okay? We can't say delta x is 0. Okay? We have to say, instead, the limit as delta x approaches 0. So as delta x approaches 0, we are getting this secant line, right? I'm going to draw different stages here of the secant line, okay? Like as delta x gets smaller and gets closer and closer to x, right? That means the distance is getting smaller and smaller and smaller. Delta x is approaching 0. Then our secant line will look something like this, right? Then our secant line will look something like this. Then our secant line will look something like this. And eventually our secant line will become the tangent line. Okay, and we have to notice that this is when delta x is getting smaller. That distance between x and x plus delta x, this x plus delta x is coming closer to this x. So that means that our delta x is getting smaller. So we can say, therefore, our m tangent, or slope of our tangent line, is literally just the limit as delta x approaches 0, right? That distance, right? X plus delta x is getting closer to x, right? That secant line is turning into the tangent line. Okay, and so that's how we can find the slope. So then of this secant line, it's getting closer, closer, closer. So f of x plus delta x minus f of x all over delta x. So this is it. This is how we get it. It's not made up stuff, guys. This is what we did. Okay, we got this crazy looking thing just from representing this y2 minus y1 or x2 minus x1 into something that is virtually the same thing. We turned an Algebra 1 concept into a calculus concept. It's really cool. It's all coming together, guys. It's all coming together. Okay, so let's go back to this problem here. So what did we actually find here? So we did this, f of x equals x squared, and we got 2x. So what does this 2x mean? Well, this 2x is essentially called our slope function. So at a value x, at the slope at a point, again, I said slope of a tangent line at a point, or like a point in the case of where it's just a general way of saying, like, okay, if you're given like a circle or something that's not a function, like x squared plus y squared equals 5 or something like that, then yes, you would have to do slope of tangent at a point, right? Like 0, 0 or something like that. But in the case here, when you're given a function, then you just do slope at an x value. Okay, slope at a particular x. So what does this give us here? 2x. Again, we're gonna call this answer. We're gonna use prime notation here. This is called Lagrange notation. We're gonna learn about derivative notation in later videos. Maybe the next video. Actually, I'm not 100% sure. But this will be called f prime of x. Maybe you've heard this prime, seen this prime symbol before. In maybe other math classes, geometry or trigonometry. But we'll get f prime of x is 2x. Okay, so that's the first derivative of f of x. So the first derivative of f of x, and again, in this case, is x squared, is 2x. So again, what does this mean? This f prime of x, this is our slope function. So we can find the slope of the tangent line at any value, at any x value. Of course, this is a polynomial, so domain is from negative infinity to infinity. So for any x value, we can find the slope at that point. So, for example, I'm going to draw our x squared again. I'm going to kind of show you here what I mean. So we draw our x squared here. Okay, I'm going to pick some random point. So let's say we have what? Let's say this is 2. This is not going to be in scale. Let's say this is 2, and then this is like 4. Okay, 2 comma 4 is a point on x squared. I want to find the slope of the line at this point. I want to find the slope of the line at x equals 2, the tangent line. I want to find the slope right here. Well, I did this, right? F of x. How do I find the slope at a point, right? I want to find the tangent line, and again, this is how we find the tangent line. Well, we establish that secant line, the f of x plus delta x minus f of x over delta x, and then we want to put delta x, limit as delta x approaches 0 of that. So again, literally, we just do that, right? Limit as delta x. That's literally what we did in the warm-up, and we got 2x. So 2x will give us the slope at any x value of the tangent line at any x value. So if we want to find the slope at x equals 2, well, we just do f prime of 2. And that's going to be 2 times 2, which is 4. So the slope of the tangent line at x equals 2 is 4. And that's, again, that is a coincidence in this case. It's not always going to be equal to the y value. Please do not take that into... don't always, that rarely happens. So again, let's pick a different example here. Like, okay, let's say f of x is x cubed. Okay, if you do this process again, you will get, like, if f of x was x cubed, f of x, you do this process again. You do this limit definition of the derivative. You do this slope. You want to find the slope of the tangent line at, you want to find the slope function. You want to find the function that gives you the slope at any x value, right? Slope of the tangent line at a function. Okay. Your f prime of x will be 3x squared. Okay. You can verify that by doing this again, but to x cubed and not x squared. There are shortcut rules, right, to this. You will not always have to use this process to find f prime of x. And For example, I know that I found f prime of x using a shortcut rule, but for now, this is all you know. Okay, this is the only way for now that you can actually find your f prime of x, or the function that gives you the slope at x value. Okay, so we have f prime of x equals 3x squared. Let me sketch out f of x equals x cubed here. Okay, so x cubed should look something like this. Okay, make sure you know your parent functions. It's important for calculus. So let's say that let's say that we have like a point here, like 1, 1. Okay, I'm just going to choose something simple. Yeah, 1 here. Yeah, 1 here is the output. And I want to find this line. I want to find this line at 1, 1. Or I want to find the line at x equals 1. Okay, this is a line. Sorry if it's a little curved. This is a line. Okay. So if I want to do that at x equals 1, well, I just find f prime of 1, and that's just 3 times 1 squared, and that's 3. So the slope of the tangent line at x equals 1 is 3, okay, for x cubed. So again, slope at a point, okay? It's also called instantaneous rate of change. We'll talk more about this in other videos, okay? This is just an intro. Okay, if you're confused still about the prime notation, don't worry, we'll talk about that. But again, for now, this is your derivative. This f prime of x is what you find. This is what f prime of x is what you get in result of doing this this limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. This gives you f prime of x. F prime of x is equal to this. Okay, so hopefully this makes sense. Hopefully this is interesting.